Welcome you all. Today we will discuss about the elementary transformations that are actually important part of matrix theory. So basically three operations we can use or we can apply on a given matrix, and these three operations are known as elementary transformations or elementary operations. The first elementary operation is interchanging of any two rows. In a matrix, we can interchange any two rows or any two columns, and this transformation is indicated either with Rij or Ri implies and implied to Rj, which means that the ith row and jth row are interchanged. And the second elementary operation is, in a matrix we can multiply all the elements of any row or any column by a non-zero scalar quantity, and this operation is indicated by KRI or RI implies to KRI. It means we have first multiply all the elements of RI by this non-zero scalar K, and then we have obtained its ith row. And the third operation is addition of constant multiplication of the elements of any row. It means we have to first multiply all the elements of any row by a constant, and then these elements are added to the corresponding elements of any other row or any other column, and this transformation is indicated by KRI plus RJ, which means that we have first multiply all the elements of ith row by K, then we have added these elements to the corresponding entries of the corresponding elements of jth row. And then by default, if we perform any one of the operation, any one of the elementary operation to a given matrix A, then the resulting matrix that will be obtained as B matrix, which is not equal to the initial matrix. So a matrix that is obtained from the given matrix A by deploying one of the elementary operation is said to be an equivalent matrix and equivalent to A. If we have performed any one of the elementary operation to the given matrix A, then the resulting matrix, which is termed as B, is said to be equivalent to the matrix A, and the equivalence relation is indicated with this notation, which means that A and B are equivalent matrices, and the matrix B is generated with the help of this matrix A by deploying or by utilizing any one of these three elementary operations. Now, elementary matrices. Elementary matrices are basically a matrix that is obtained from the identity matrix or unit matrix by utilizing or by deploying any one of the single elementary operation. Suppose this is identity matrix of order 3. If we apply a elementary operation which is R2 implies to R2 plus 2R1, what does it mean? That it means that first we have multiply all the entries of R1 by 2, then we have added these elements to the corresponding elements of second row, that is R2 row. That means first we have multiplied the R1 by 2, then the entries will be 2 0 0, then we have added these elements to the corresponding entries of second row, that is 0 plus 2, that is 2, 1 plus 0, that is 1, 0 plus 0 equal to 0. It means this matrix is obtained from the identity matrix by utilizing this elementary operations. Therefore, this resulting matrix is said to be an elementary matrix. And with the help of this example, we can easily see that how the elementary transformation can be utilized to a matrix. Suppose here the question is, we have to reduce this matrix to the upper triangular form. Upper triangular form is basically a form in which all the entries below the leading diagonal are 0. So our objective is to reduce this entry 1, -1 and -1 into 0. Then that resulting form will be our required form, which will be upper triangular form, and we have to deploy the elementary transformation. So first, in order to reduce this entry 1 into 0, we have used this row. So the corresponding operation can be used as R2 row, that is second row is replaced by R2 plus R1. It means we have added these two rows, and this is actually our third elementary operation, which is basically we can add the elements of any scalar multiple of any row to the corresponding elements of any other row, and this -1 is again reduces into 0 with the help of this -1 by using the operation R3 minus R1. Therefore this entry becomes -1 minus -1, that is 0. So the resulting matrix is first row remain as it is, as we have not used any operation in this row. Therefore the first row is same as -1 2 -1. In the second row, now the second row is replaced by R2 plus R1. So therefore the resulting row is 1 plus -1, that is 0, 2 plus 2, that is 4, 1 minus 2, that is -1, and the third row is replaced by R3 minus R1, that is the corresponding entries are -1 plus 1, that is 0, -1 minus 2, that is -3, 0 plus 2, that is 2. Now these two entries become 0. Now in order to reduce this triangular form, our objective is now to reduce this entry -3 into 0 with the help of some suitable elementary transformation. Apply this operation, which is R3 is replaced by R3 plus R2. R3 plus R2, then the changes will become in third row. That is the first two rows will remain as it is. That is the first row -1 -1 2 -2, second row 0 4 -1. The third row we have applied this elementary operation, which is R3 plus R2. R3 plus R2, so the entries will become 0 plus 0, that is 0, -3 plus 4, that is 1, 2 minus 1, that is 1. Now in the next case, we are using the operation that R3, because our objective is to reduce this entry into 1. So this entry can be reduced into 1 with the help of this entry by using the elementary transformation. It means R3 third row is replaced by R3 minus 1 over 4 times of R2. Then using this operation, this entry will become 0 and the corresponding entry is 5 by 4, which now this form is our upper triangular form. This matrix can be further simplified by removing the fractional entries in third row by simply utilizing the operation that R3 is replaced by 4R3. So this matrix is obtained, which is our required upper triangular form. This is also upper triangular form.